Okay, well, I guess we better dive on in, even though there's only a few people here. So we have a lot of logistics that we need to discuss because we're coming up on the final stretch of the semester. So I have some updates for you. For one, I called in some backup on grading homework 4. So you may have noticed that those grades have been uploaded to Canvas now. I took it home and printed it out on paper. So I still have to scan and upload these back to Canvas so you can see where the mistakes are. But I will do that today. So homework 4 is taken care of. Here's where things stand for the remaining 3 outstanding homeworks. 5 was already taken care of. And so we're talking about homework 6, 7, and 8. I've got 8 out of 13 in hand for homework 6. And for homework 7 and 8, I have 4 apiece. So clearly people need some more time to work their way through this. And this has bearing on when we plan on holding the midterm, which has bearing on when I have to cut off homework submissions so that you guys have a chance to go over the solutions to study. Assuming, of course, that having the homework solutions was actually helpful for you on midterm number 1. The exam was a little bit different format from the homeworks and things, although things changed up a little bit after that. So I'm questioning everything at this point, including, is it necessary for me to post the solutions for you guys to prepare for the exam, given that you'll have the sample exam? What I don't want to do is lock people out of this when you clearly still need more time. So regarding the midterm, we have 1 more week's worth of material to discuss this week on scattering theory. So today we will wrap up scattering theory beyond the Born approximation, which is beautifully encoded in Feynman diagrams, which I think sets us up very nicely for calculations that will be done in quantum field theory next year. The last topic that we need to cover probably on Wednesday is scattering lengths and phase shifts. This is the last topic that I am aware of at the end of the book that has been on recent comprehensive exams. So I want to make sure that we go over that. So given that I need this week to finish going over the material, next week is the likely date for the exam. And so the way I'm looking at it, we've got basically 3 choices. If we proceed with the schedule in some sort of rigid format, that would mean this week we finish out everything. This weekend, I somehow borrow time from the uncertainty principle and manage to prepare a sample exam on top of everything else. And we would do the sample exam next Monday. The exam would be next Wednesday. And then next Friday, I would issue the regrade. And you would have a week or so to do that. If this is the timeline, then that means I probably need to cut off all homework submissions by this Friday so that you will have all solutions in hand to study by for the midterm next week. I'm looking at this going, I don't know how I'm going to do that because this weekend is like a delta function singularity for me with giving talks and sharing sessions and all kinds of other stuff. So it would be real appealing to me to shift this back by at least 1 class. If I shift it back by 1 class, then perhaps Monday can be a practice session. I think we will have finished all new lecture material by that point. And maybe that can just be a recitation time to discuss questions about the homework, other simple examples, anything that you guys need to practice and prepare. And then that would push the sample exam to Wednesday and then the actual exam to Monday the 26th. If that's the case, then I can push back this timeline a little bit, and instead of cutting off homework on Friday, I could cut it off perhaps on Monday. That would give you guys the weekend to try and catch up as well. Option C, I guess, is the nuclear option, which is to say, do we really need to have a second midterm at all? I feel like having a second midterm is advantageous for you guys to have another exam grade to help dilute anything from the first exam or the midterm, the first exam or the final. But if it's a question of how to squeeze it in and a cost-benefit analysis, I'm not entirely sure that the benefits outweigh the costs. So I want to get your feelings on this. This is sort of the agenda that I'm looking at, and depending on how we pick this, that will determine how many lectures worth of new material that we can cover. I think in any of these scenarios, we have at least enough time to cover the last 1 lecture, which is absolutely essential for the things that you will need for the comprehensive exam, which is identical particles and the variational principle. So we may not get into those things in great depth, but we can at least practice them a little bit so that you will have those in your toolbox for the comprehensive exam. The material that we might sacrifice is sort of more of the big concept. What are the limitations of quantum mechanics, and why does one need to go to quantum field theory? Personally, I would really like to be able to talk to you about that, but if there's no time, then there's no time. I can always put a video online, and if you want to watch it, you can watch it. So this is what the landscape looks like to me. What are your thoughts and comments on this?
I agree that the homework cutoff this Friday sounds pretty unrealistic, at least for me.
Yeah, I agree that this is probably pretty unrealistic for most everybody given these numbers. And I don't want to lock anybody out of being able to do, like, this is the most important stuff. This is the core material that we've covered in the second half of the semester. I do not want to shortchange this for the sake of squeezing in an extra exam if that's not going to benefit everybody. So what about people online? Do people tend to agree that option A is pretty unlikely?
That is correct.
I can't hear you very well.
I agree that option A is unlikely, and I am a proponent of option C.
Say again?
I think option A is unlikely, and I am a proponent of option C.
Okay, so this is not a formal vote. This is just me taking down people's opinions on things. So I'm hearing one person in favor of option C and a couple of people against option A. What are other people's thoughts?
I think option B would be good. Option A does seem a bit rushed or unrealistic as well.
I agree.
So I think option B may be the best.
But you would prefer to still have a second exam to help dilute the grades a little bit?
Yes, it could be better. More practice is better in the long run.
Okay.
Yeah, put me down for option B.
2 votes for option B.
Dr. Siebert, I also support the option B unless the final exam is comprehensive. And if the final exam is not comprehensive, then option C is good.
Yeah, so the final exam I would like to be comprehensive. I would like it to cover everything for the entire semester because that is my chance to summarize everything we've gone through and make sure you have all of the tools that will be necessary for the comprehensive exam. So I think that's the best, I don't know how to say it, let's say vaccine against the comprehensive exam that I can give you with all of the necessary antibodies so that you will be able to go into that thing with the tools you need.
Okay.
Okay, any other thoughts on this topic? I don't want to make any decisions now live. I just wanted to sort of take the temperature of the room. You're welcome to send me emails afterwards if you would like to speak in private. I care about everybody's opinions on this because, like I said, the point is to give you guys practice and exposure to the material, and I don't think anyone benefits from shortchanging this to try and rush something like that. Personally, yeah, this seems very unreasonable for you guys to catch up, and it seems unreasonable for me to try and do a good job of preparing the sample exam. If I have at least through Monday, then between Monday and Wednesday, I can actually take my time and try and synthesize something better for you guys in terms of the sample exam. So my preference would also be not A, probably B, and depending on whether you think you need it, option C would potentially buy us a little bit more time to discuss, but maybe the costs outweigh the benefits for that.
Okay. Chance of a hybrid option B where we cut off homeworks on the 21st? Because I feel like 5 days after that to the midterm is a good amount of time to have all the homework solutions plus the sampling and do a bunch of study.
That's a good point. Yeah. So mostly I want to make sure you have at least a few days with all of the the homework solutions in hand to study by. You're right. So I had been cutting this, like if the exam was going to be on a Wednesday, then I wanted to cut it off by the Friday before. But yeah, if this is now going to be the midterm on Monday, then maybe this is enough time. So yeah, maybe instead of cutting it off on Monday the 19th, we could consider cutting it off on Wednesday the 21st. And that would give you guys a little bit more time as well.
So for option C, is there maybe a potential where instead of an exam, there's some sort of maybe a short review homework that, like, I don't know. I think the biggest thing is, like, if we could have, like, homeworks give us a longer time, and so it's like less stress, but perhaps the due date could be a strict time.
So you're thinking instead of an exam, which is supposed to cover this stuff, you're thinking of a review homework. I would still want to set it up in the format of an exam. So right, the homeworks have been sort of long form problems, and I like the fact that the exam was testing the short concepts and basic calculations that are most necessary, but you're proposing a summary homework 9, let's say, that we can say it's essentially the midterm. It would be essentially the same kind of content as the midterm, but not given in class, given as a take-home, let's say.
Right. Yeah.
Okay, that's another possibility. Midterm as take-home, ? / super homework. What are thoughts on that? That would free up the calendar a bit if we don't try to do the midterm in class. It would, presumably if we did that, then that would also short circuit this process of sample exam, regrade. If this is some take home thing, then I don't need to design like 3 different copies of it. I can design one and you can take your time and work through it. And that would be more practice than assessment. Thoughts on that?
I like that idea.
You like that idea?
I think that works.
Yeah,
Okay.
I think also that works for me too.
Okay, so I'm hearing a lot of positivity around this idea. Okay, thank you for the input. Any other comments before we shift on? I think what I will do is I will try to summarize this discussion in an announcement on Canvas. And I'll think of some way, maybe I'll open it up as a vote or a poll on Canvas, or maybe I'll just open up the discussion on that announcement, but I want to propose what we've discussed here and ask for comment online before coming to an official decision.
If we were to do a midterm super homework take home,
Yes.
When would that be due by?
I would probably, my instinct is to say the end of the semester, honestly. If the point of this is to do the under pressure timed drilling practice so that you've got it on command. If we're doing it as a take home instead, then the purpose is different. So I don't see any point in making a rigid timeline for this if instead of doing the rigid drilling, we're just going to take home and practice so that you've got a study guide essentially. So I would be inclined to give it a deadline along with a super homework and say, I could put a deadline online, but I'm not going to penalize you for it until I have to cut off everything at the very end of the semester, which is probably the 30th. So we're still not talking about a massive amount of time here. We're still only talking about a couple more weeks. But this would be a synthesis assignment, sort of similar to if I gave you the sample exam as a take-home or the midterm as a take-home.
Is there any chance we could do either a practice session, some similar problems to what we'll see on the final, say, or on the comprehensive exam?
Yes.
The super homework thing.
Yeah, so this cutoff on the 30th is reserving the very last week to do nothing but, I see, sorry, Mohammed, I see you don't have a mic on. Yeah, so this cutoff is still reserving the very last week of class to do nothing but review. So my intention is no matter what to give you week-long sample exam to prepare for the final in class that last week. And then during finals week, you will have the actual final class. Okay, thank you guys. I appreciate the discussion. It sounds like this is the heavy favorite with some amount of support for this idea as well, but nobody really likes this option, myself included. Okay, cool. Any other housekeeping stuff that we should discuss before we dive into the physics? Okay, fantastic. All right, so the last couple of weeks, we've been discussing scattering theory. We've done the basics of scattering theory. So the key picture associated with scattering theory is that you have some incoming particle which is associated with a plane wave. So you have momentum P initial, which is H bar K initial, described by the plane wave, e to the I k incoming dot r. And usually we pick this k incoming to be along the z-axis. So usually we will write this as e to the I kc. That incoming plane wave or incoming momentum state scatters off a potential. Most of the time we will consider potentials that are spherically symmetric. So I will write v of r vector, but most of the time we're really going to be concerned with spherically symmetric potentials v of r scalar. And then we look at the answer which describes an outgoing spherical wave. That outgoing spherical wave goes in all directions, and we can ask how much of that spherical wave is going in a particular direction. E final, which is h bar k final. So mathematically, what we said is that this is described by the asymptotic form of the wave function. We describe this as a boundary value problem at infinity for the time-independent Schrodinger equation. So we say as r goes to infinity, this wave function should separate out into two contributions, one from the incoming plane wave, one for the outgoing spherical wave. So there should be psi incoming of r plus psi scattered of r. And up to some overall normalization constant, I pull that out, say the normalization of the incoming plane wave. This is e to the I k incoming dot r plus some amplitude, the scattering amplitude f of theta and phi, e to the I k r over r. So this is the definition of the scattering amplitude. All right, in terms of this, we calculated the scattering cross-section, the sigma d omega, which, let me remind you, is defined as 1 over the incoming current times the differential rates. The reason for defining this funny object called the cross-section is because different measurements depend on different beams. If I send in more particles, I get more rate out. So the part which is experiment independent is the transition rate per unit beam, which has dimensions of area and is called the cross-section. From this expression, we worked it out, and by looking at the probability currents, we found that this is exactly equal to the scattering amplitude squared. Absolute value squared, which means that this is f star f, which is a whole lot like saying that probability is psi star psi. So the basic object in scattering theory is the scattering amplitude. It is analogous to a wave function, and the observable is proportional to the scattering amplitude squared. We said that the scattering amplitude is often written in terms of the momentum transfer vector q. F of theta and phi is f of q vector, where h bar q is defined to be p final minus p initial. And this encodes information about the scattering, right? So h bar q is how much momentum you absorb from the potential. That tells you the difference between the incoming momentum and the outgoing momentum. So that obviously is related to the angle of scattering. So if the incoming beam is along the z-axis here, then that deflection here, theta, and maybe even a deflection phi in the azimuthal plane, comes out from the momentum transfer vector q. So we saw by squaring this that h bar squared q squared was equal to 4 p final squared sine squared theta over 2. And since momentum is conserved, or the magnitude of momentum is conserved, this is just related to the total energy. 8 energy mass sine squared theta over 2. Is this legible enough for you, Nicholas? I know I tend to write small sometimes in the bottom.
Yes, thank you.
Sure. Okay, so the momentum transfer Q is proportional to the energy, or Q squared is proportional to the energy, and it encodes the deflection angle theta. This is the magnitude of Q. The vector direction of Q will tell you about the angle phi. But if the potential is spherically symmetric, then there will be no dependence on the azimuthal angle phi. It will just depend on the Q squared. Okay, so this is sort of the overall setup of the problem as a boundary value problem. If you solve the time-independent Schrodinger equation by hook or by crook, then you can figure out what the scattering amplitude is. And knowledge of the scattering amplitude gives you the cross-section. You can try to do it exactly by boundary value problem, or you can try to do it order by order in perturbation theory. So solve boundary value problem of the potential So this is very similar to what we did in one dimension, where we said I have some potential v of x, and you would solve the wave equation in one side, solve the wave equation on the other side, and at the interface, you would enforce things like continuity and differentiability. This is really only possible for particularly simple potentials. So you can do it this way if you have a spherical square well, for example. But if you have a Gaussian potential, good luck with that. So instead, one can try to solve order by order in perturbation theory. Order by order perturbatively in the potential V. At lowest order, which is sometimes written as LO lowest order or leading order, that corresponds to the Born approximation. And we found that the scattering amplitude f of q was just negative m over 2 pi h bar squared, Fourier transform, d3r, e to the minus I q dot r, v of r. So if I go back to this picture of the scattering process, let me draw the Born approximation to it above. So you know the overall amount of momentum transfer must be h bar q. You came in with momentum p initial, you went out with momentum p final. Overall, you absorb the difference p final minus p initial is h bar q. In the Born approximation, you absorb that momentum transfer in 1 unit, exactly 1 interaction with the potential that provides the missing momentum. So if there is exactly 1 insertion of the potential, then this process looks like exactly 1 interaction with the potential that takes you from P initial to P final, which is equal to P initial plus H bar Q. And you get there by absorbing momentum H bar Q from the potential, and that depends on that Fourier transform potential V tilde of Q. So if I came in with 1 unit of momentum, I go out with 3 units of momentum, then I look at my potential, I find how much of it has 2 units of momentum by Fourier transform, and that's my scattering amplitude. So obviously this is only true at lowest order in perturbation theory. If you interact with the potential exactly once, you have to take 1 big bite of momentum and absorb it all together. At higher orders in perturbation theory, you can build up the total momentum you measure in multiple smaller units. And so the question is, how do you generalize this? How do you go beyond the Born approximation? For practical purposes, in terms of things that you will need to do under pressure, such as on the comprehensive exam, this is probably the limit of it. So if you are preparing for the comprehensive exam, study this part, make sure that you can take a random potential that somebody throws at you, Fourier transform it, calculate the cross-section. What I am showing you the second half of last class and today is how to put this in a bigger framework to understand how scattering theory works more generally, to set you up for future success. So we started discussing that last time, how to go beyond the Born approximation. And the method that we are using to attack this problem is the method of Green's functions. Let me also remind you, we did a particular example last time. We did the Yukawa potential. V of r was g e to the minus mu r over r, and we compared that to the Coulomb potential. V of r was g over r, which is just the Yukawa potential in the limiting case mu equals 0. In this example, we Fourier transformed the potential, and we found the scattering amplitude f of q was minus 2gm over h bar squared 1 over q squared plus mu squared. And the defining feature of this Fourier transform is that it has lots of low momentum modes. Low momentum modes, which corresponds to the long distance tail of these spatial potentials. Because of this, the overwhelmingly dominant part of the cross-section was scattering at low angles. When you calculated d sigma d omega, we got 4g squared m squared over 8me sine squared theta over 2 plus h bar squared mu squared squared. And so this is dominated by small angles theta. So all of these pictures are linked. I want you to see clearly how, given a particular function, you Fourier analyze it to pick out how much momentum is there at high momentum and low momentum. This particular potential has lots of low momentum modes, so it generates a cross-section that is predominantly forward scattering, very low angles. So for potentials that are more concentrated at short distances, then you will have more hard scattering events and less soft scattering events. Okay, and so now setting up going beyond the Born approximation. We discussed the method of Green's functions, which are essentially a way of implementing the perturbation series as an integral equation exactly the same way we did for the time evolution operator, but this is not in time, this is in space for the time independent equation. So we said, if I have a Green's function g, then I can construct the full solution, order by order in perturbation theory, psi naught of r plus 2m over h bar squared integral d3r, Green's function of r minus r prime, potential at r prime, initial condition at r prime. That's first order. One insertion of the potential, one insertion of the propagator. At second order, there are two of them. D3r, D3r prime. And I have a propagator that takes me to r from r prime, potential at r prime, another propagator that takes me to r prime from r double prime, another potential at r double prime, initial condition at r double prime, and so on and so forth. So this encodes the first order answer, which ought to reproduce the Born approximation that we already know, plus a systematic scheme for going to higher orders at any accuracy we need. So this is how a Green's function can help us. The last thing we did last class was to find what that Green's function is. For the free particle, and actually not even the free particle, for the time-independent Schrodinger equation in 3 dimensions. We wrote that equation as Laplacian plus k squared. Psi equals 2m over h bar squared v psi. So a Green's function for this operator would be one for which Laplacian plus k squared, Green's function of r, is delta function of r. And because the Schrodinger equation is a linear equation, knowing the solution for a point source allows me to construct the solution for any source by a superposition of delta functions. We solved this equation by Fourier transforming this equation into momentum space. And what we found was, dr is the inverse Fourier transform d3q over 2 pi cubed e to the I q dot r. And the Fourier transform was 1 over k squared minus q squared plus I epsilon, where this k squared is 2m e. So this is sort of how much momentum you're absorbing from the potential, how much energy there is. This thing becomes singular. The term is on shell. If you think of this as like the equation for a sphere in 3 dimensions, This thing becomes singular when Q squared is equal to K squared. That is referred to as the energy shell or the mass shell. K squared equals Q squared, so this is sometimes called on-mass shell. The term comes more from the relativistic case where you include the rest mass energy as well, but this is essentially the same physics. So this then becomes singular when the momentum corresponds to the actual energy you really have in real life. And so in order to regulate that, we needed to introduce an I epsilon regulator to determine where the poles are in the complex plane. There are multiple ways to do that. This particular choice plus I epsilon was the one that gives us the outgoing spherical wave we needed. Plus I epsilon regulator leads to outgoing spherical wave. And so we evaluated this Fourier transform using residues. Now using that I epsilon to shift the location of the poles so we know which one we pick up when we close up versus closing down. In doing so, we found the solution G of R was minus 1 over 4 pi e to the I k r over r. And that e to the I k r is exactly the one that we wanted because that corresponds to the outgoing spherical wave. So now that we've set up the problem, we know how to use a Green's function to find the general solution. We have found the Green's function, now we can just plug it in and calculate. And we want to take this expression and determine its behavior as r goes to infinity in order to find the scattering amplitude and match the boundary conditions at infinity. Okay, so picking up where we left off, the next step is to use G of R to match boundary conditions at infinity. And matching the boundary conditions on the spherical wave allows us to find the scattering amplitude f of q. Okay, any questions on the review from last time before we pick up where we left off? Okay. So I'm going to start with this expression. Let me just work to first order for now in the potential, and let's verify that we reproduce the Born approximation. So if I write psi of r equals psi naught of r, this is any free particle solution with potential equal to 0, plus 2m over h bar squared integral d3 r prime. Now I have the Green's function with argument r minus r prime. So I get e to the I k r minus r prime magnitude divided by r minus r prime magnitude. I get minus 1 over 4 pi in front. So let me put this out front here. Minus 2 pi. Sorry for proof by erasure. I had 2m over h bar squared, and I combine that together with a minus 1 over 4 pi to get negative m over 2 pi h bar squared. That's the Green's function. I have my potential v of r prime, and I have the initial condition psi naught of r prime. And this is just the first order expression, so this is accurate up to corrections of order v squared. So this is already starting to look like the formula we had for the scattering amplitude. You see now why that factor negative m over 2 pi h bar squared shows up. It's the combination of the expression converting from wave number to energy, 2m over h bar squared, together with the negative 1 over 4 pi from the Green's function. What I need to do next is take the r goes to infinity asymptotics of this. So I need to examine what happens to the Green's function here as r goes to infinity. Now, not r prime. R prime is some point where there's a potential. If the potential is localized, if it doesn't have infinite range, then this is sitting somewhere close to the origin. So r prime is not necessarily going to infinity, but r is. So I want to expand this for the limit when r is much greater than r prime. So the idea is r prime equals where there is potential i.e. where the target is, something localized in space. R is equal to far, far away. So we want to expand both this numerator and this denominator in the limit when R over R prime is large. That will help us find the asymptotics and match on to the scattering amplitude. All right, so how do I do this? First, let me tackle this denominator. I have 1 over absolute value R minus R prime. So in terms of the vectors, R and R prime, this is equal to R squared plus 2 R dot R prime plus R prime squared to the power negative 1/2. Right, so this is, minus here, not plus. This is R minus R prime vector quantity squared. And then I take the negative 1/2 power to bring it down into the denominator and make it a single magnitude rather than magnitude squared. So with this, let me pull out the leading behavior as R goes to infinity. So I pull out R squared and I raise it to the negative 1/2 power. So I get 1 over R. And I'm left with 1 minus 2 R dot R prime over R squared plus R prime squared over R squared to the negative 1/2 power. Now I've got the leading power is 1. Both of these objects are small, but how small are they, right? So this is 2, negative 2, R vector over its magnitude. That's a unit vector. Dot product with R prime over R. So this term altogether is 1 power small, order R prime over R. Right? R vector over R is order 1. But R prime is something trapped near the origin, and R prime is getting big. This is a small number, so this is first order small. This term, on the other hand, is second order small. R prime squared over R squared. So that will determine what we get when we expand this out. So now I open up the parentheses using the binomial theorem. This is approximately equal to 1 over R times 1 minus. I get minus and then another minus 1/2 from the binomial theorem. So I get plus R dot R prime over R squared. Plus corrections which are order R prime squared over R squared. So this one was pretty simple. My leading behavior is 1 over R. The correction to that is R dot R prime over R cubed. So plus order, let's say, R prime squared over R cubed. Something like this. So the important part about this is that this leading behavior is 1 over R and everything else about it is small. So I'm not going to worry about this. I'm not going to worry about this. For the denominator, the only piece that I need to keep as R goes to infinity is the 1 over R behavior. It's not going to be so simple for the exponent, where the power is positive instead of negative. So in the exponent, we have e to the I k R minus R prime. Now we'll do a similar exercise here. R minus R prime is equal to R squared minus 2R dot R prime plus R prime squared to the positive 1/2 now. Now I pull out a positive factor of R, 1 minus 2 R dot R prime over R squared plus R prime squared over R squared to the 1/2 power. Now I open up the parentheses and I get R 1 minus R dot R prime over R squared plus corrections that are second order small, R prime squared over R squared. So the important part now is that when I expand this thing out, I get R, which is going to become e to the I k R. That's the outgoing spherical wave that we want, but this piece is not small. This piece is minus R dot R prime over R. So everything else is small, it's suppressed by the small quantity. But this is just a unit vector. This knows about the direction. R over its magnitude R dot R prime. So when I expand this thing out, I get the outgoing spherical wave and I get something that knows about the direction of R but is not otherwise small. So I get e to the minus I k R vector over its magnitude, which is something like e to the I k R, e to the minus I k dot, if you'll forgive the abuse of the hat notation, this is not an operator, this is a unit vector, this is e to the minus I k dot R hat. So putting it back together, we have psi of R asymptotically as R goes to infinity becomes psi naught of R at asymptotic infinity minus m over 2 pi h bar squared integral d3 R prime, and then my Green's function was e to the I k R e to the minus I k dot R hat. And 1 over R from expanding downstairs, times the potential at R prime times the initial condition psi naught at R prime, plus order B squared corrections. Okay, we're almost there. The last step is to recognize that this object e to the minus I k dot R hat is e to the minus I k final dot R. Or if you like, e to the minus I p final over h bar dot R. So we said, here was the potential. You have some outgoing spherical wave. This is going in the direction of R, and its magnitude is p final, which is h bar k final. So if this has magnitude k, and it's pointing in the direction of the observer at point R, this is the final momentum. So what we have found is this one is e to the minus I k final dot R. And now if I plug in my initial wave, incoming wave, psi naught of R is e to the plus I over h bar p initial dot R. So if I now plug in the last missing piece, which is this incoming plane wave, which also acts as the source for the Green's function. And what I get is psi of R asymptotically goes to e to the I over h bar p initial dot R minus m over 2 pi h bar squared integral d3 R prime. Now I've got two phase factors. I've got this one, which is this, and then I've got the initial wave function, which is this one. So if I put them all together, this is e to the minus I over h bar p final minus p initial dot R prime v of R prime. And now this is multiplying the outgoing spherical wave e to the I k R over R. This R is independent of the integration. The integration is R prime over everywhere there's some potential. This describes the outgoing spherical wave. So this object in brackets, including the minus sign, I guess, is exactly the scattering amplitude. It's the ratio of the outgoing spherical wave magnitude to the incoming plane. So this allows us to determine using the method of Green's functions, which then we can systematically generalize the scattering amplitude f of q is minus m over 2 pi h bar squared integral d3 R prime e to the minus I q dot R prime v of R prime plus order v squared. So this correctly reproduces the Born approximation. And it is generalizable. So by finding the Green's function, we had already done everything. The only step that we needed to do last was study what happens to that Green's function asymptotically. If I take e to the ik r minus r prime over r minus r prime, and I stretch it out so one of the coordinates go to infinity, then the dominant part becomes the outgoing spherical wave, which is what determines the scattering amplitude. And left over from this correction was the knowledge of the outgoing wave direction, e to the minus I k final dot r. And that combination of Green's function produces spherical wave, Green's function produces outgoing momentum states, together with the incoming momentum state that we put in, gives us exactly the Fourier transform that says I got to momentum p final starting from momentum p initial by absorbing a momentum mode from the target. Is it clear how we arrived at this and reproduced the Born approximation using the Green's function method? Because now we're going to go to higher orders. The part about this which is really beautiful is that this is totally systematic. It's so systematic that you can articulate a set of rules called the Feynman rules and then just blindly apply them without necessarily even knowing where they come from. So now let's take it to second order. Calculate the contribution to the scattering amplitude f of q, not including the first order. Let's just only calculate the second order. So I'm going to write f of q evaluated at order v squared, because I just don't want to copy down the piece we already did here. The term that comes at second order from iterating this twice was, let's see, 2m over h bar squared d3r prime, d3r double prime. We had Green's function that propagates you to the final point r from r prime. We had potential at r prime. We had another propagator, Green's function that takes you to r prime from r double prime. We had another potential at r double prime, and we had the initial condition at r double prime. So what's going to happen? I'm going to take this expression. I guess maybe I shouldn't put equals here yet because I have to pull out the overall spherical wave before I can say that this is equal to the scattering. Where's that going to come from? Exactly the same place as before. I'm going to take this expression. R prime and R double prime are localized. They're somewhere trapped near the origin. But R is going to infinity compared with the asymptotic. So I'm going to take this particular Green's function, the last one, and I'm going to stretch it out so far that it breaks. This one is going to get replaced exactly the way that we did before. This is going to give me minus 1 over 4 pi e to the I k r over r, and it's going to give me e to the minus I k dot r, the outgoing spherical wave in a particular direction. We call this k final dot r. So if I take the asymptotic limit of just this last part of the Green's function, and then I get rid of the outgoing spherical wave, that part gets absorbed into the normalization of defining what is the scattering amplitude. Everything that's left is going to give me the scattering amplitude after I remove that outgoing wave. So now I can put the equal sign there. F of q evaluated at order v squared. And let's plug in what the Green's function is. So I have 2m over h bar squared d3r prime, d3r double prime. I've pulled out the spherical wave, and I'm left with just minus 1 over 4 pi e to the minus I k final dot r. That's all that's left of this last Green's function propagating me out to infinity. Everything else stays fully intact. So I have a potential at point r prime. I have the complete messy propagator, which is not asymptotic. E to the plus ik r prime minus r double prime over absolute value r prime minus r double prime times another potential v of r double prime times the initial condition. The initial condition psi naught of r double prime. was just my plane wave. This was e to the plus I k initial dot r double prime. So the endpoints behave the same way as before. There's just some more complicated integrals in the middle. The last endpoint generates the spherical wave, and it generates the outgoing momentum state, e to the minus I kf dot r. The initial condition generates e to the plus I k initial dot r double prime. This is r prime. These are at different points. So what I'm left with, you'll notice this minus 1 over 4 pi and another minus 1 over 4 pi automatically combine with the coefficients in front. So I just get two factors of that minus m over 2 pi h bar squared. And I've got integrals over r prime, r double prime. For the outgoing state, I have the plane wave, e to the minus I k final dot r prime. And then in between, I've got potential at r prime, propagator to r prime from r double prime, another potential at r double prime, and then I have the incoming wave, e to the plus I k initial dot r double prime. So what this describes, I already wrote this as e to the I k r prime minus r double prime over r prime minus r double prime. This is about as simple as the expression gets in coordinate space. So both r prime and r double prime are both small. There's nothing else asymptotic going on. If you want to know the exact answer to this, you need to calculate the exact integral, which is complicated for a given potential. But if you could do it, you would plug in for what this potential is, you plug in for what that potential is, and you would take essentially a double Fourier transform with a propagator in between. The fact that this thing is messy in coordinate space is a way of telling us that this is actually something that should be viewed in momentum space. We said that the first order approximation, the one that we derived before, corresponds to going from k initial to k final by absorbing exactly 1 unit of momentum. This is going to correspond if I transform the potentials. This is going to correspond to absorbing 2 units of momentum, 1q and 1q prime. So the better way to view this problem is in momentum space. In coordinate space, when you go to higher and higher orders, you get more and more integrals. Yuck. But if you go to momentum space, integrals become products. That's much, much easier to deal with. Here in momentum space. So we already know what the Fourier transform of my Green's function is. We solved for this thing in the first place by Fourier transform. So we know that so I guess that includes the minus 1 over 4 pi. Let me make sure I'm not performing my factors here. Yeah, it looks like the notes I probably did fumble with factors of 4 pi there. So I know that e to the plus I k r prime minus r double prime over r prime minus r double prime is, let me put that negative 4 pi back before I forget it, because this thing originally for the Green's function had a negative 1 over 4 pi in front. And this was integral d3q over 2 pi cubed, the Fourier transform, e to the plus e to the plus iq dot r prime minus r double prime, and the thing in momentum space was 1 over k squared minus q squared plus I epsilon. So if I insert this transformation here into this expression, it's going to convert the entire thing into momentum space. So what I get is the second order contribution to the scattering amplitude, order v squared, is, let's see, I had minus m over 2 pi h bar squared. Now I've got 3 sets of integrals. It looks like my life just got more complicated because now I introduced another d3q over 2 pi cubed. And I still have D3R prime, D3R double prime. But what I'm left with is exactly this. I have e to the minus I kf dot r prime, potential at r prime. In between, from the propagator, I had negative 4 pi so that I don't forget it. And then in the denominator, I have k squared minus q squared plus I epsilon. This comes with its own Fourier factor, which I'm going to write as, let me put that one over here, e to the plus I q dot r prime times e to the minus I q dot r double prime. Yes. And then I have the potential v of r double prime, and I have the outgoing wave e to the plus I, sorry, the incoming wave, k initial dot r double prime. So all I did was I took this expression and I split up this Fourier factor. This is really a product of two. And I took the r prime one and I put it here next to v of r. And I took the r double prime one and I put it here next to v of r double prime. Now, what do I get when I do the integral over r prime? The only thing here that depends on r prime is that. This is a Fourier transform of the potential to momentum space. Likewise, when I do the integral over r double prime, the only thing that that talks to is this one. So this is translating the picture into momentum space for us. That first box here, when I Fourier transform, this is going to give me v of, and then r prime becomes k final minus q. And when I integrate this one, I'm going to get v in momentum space of q minus k initial. Make sure I got my signs right. Transform it to e to the minus I. Yes, k final minus the intermediate. Great. So what I get in momentum space is a lot cleaner. F of q, and maybe I shouldn't call this q if I'm keeping q for the external one. Let me call this k prime so that I'm not repeating indices here. K prime, this is now k prime squared. K prime, so now this is k final minus k prime, and then k prime minus k initial. Sorry, apologies for reusing q's here. So at second order, what I get is now something intelligible. There were two of these factors to begin with. I shouldn't drop them. Right, so I got minus m over 2 pi h bar squared squared. I now have integral over the intermediate momentum k prime over 2 pi cubed. And then everything else is a simple product of factors. So I get a momentum space v of k final minus k prime. I have the propagator in momentum space minus 4 pi over k squared minus k prime squared plus I epsilon. And then I have the momentum space potential again of k prime minus k initial. And so I think the last step that I'm going to do is I'm going to associate these two factors with the two potentials. So there are 3 ingredients to this expression. An integral over the intermediate momentum. Each time I have the potential, it comes with a factor of minus m over 2 pi h bar squared. Fourier transforms potential, k minus k prime. In between them, I have a propagator in momentum space, k squared minus k prime squared plus I epsilon with a minus 4 pi. And then I've got another factor of the potential, minus m over 2 pi h bar squared, v of k prime minus k initial. So let's draw the picture of what this looks like, and let's associate these numerical factors with each of those elements from the diagram. So at our scattering amplitude, we said f of q. At first order, it looks like I absorb 1 unit of momentum from the potential. I have, let's say, incoming momentum h bar k initial, and it goes to h bar k final, which is equal to h bar k initial plus h bar q. And the way we got there was by absorbing momentum h bar q, and that scattering amplitude came with a factor minus m over 2 pi h bar squared Fourier potential of q. This was first order. Now we have the expression at second order. It looks like there are 2 insertions of the potential. I come in with h bar k initial. The first potential here is, I read it backwards. So this is delivering momentum k prime minus k initial. So this one is carrying h bar k prime minus k initial. So if I started off with h bar k initial, this line in between has momentum h bar k prime, some intermediate, undetermined momentum. This potential came with the factor minus m over 2 pi h bar squared, Fourier potential of this momentum, k prime minus k initial. Then the second potential adds momentum, this is the one, k final minus k prime. So this one is delivering h bar k final minus k prime. If I add that to h bar k prime, I get exactly the measured h bar k final. This one again came with its own factor, minus m over 2 pi h bar squared d tilde of k final minus k prime. And now because we know the Green's function, we know exactly how they get connected from one to the other. The propagator from here to here came in from the Green's function, which was minus 4 pi over k squared minus k prime squared plus I epsilon. And at the end of the day, I started off with this momentum, I ended up with that momentum, and in between, I could have transferred any amount of momentum through this loop that I want. So the last step is this integral over all unconstrained momentum. I fix the initial state, I fix the final state, but anything in between can happen. And in quantum mechanics, everything that can happen does happen. So the point is, you can think about the scattering process unambiguously by drawing diagrams like this. And it's unambiguous because every element of that diagram can be uniquely associated with this integral, this factor for the potential, this factor for the propagator, or this factor for the potential. So the building blocks of any scattering amplitude are expressed in terms of the Feynman rules. Every time you have the insertion of a potential, anything that takes you from some h bar k1 to some h bar k2, and it's interacting with the potential. That means it's absorbing momentum, h bar k2 minus k1. This always comes in with that corresponding factor. So anytime you have an interaction with the potential, you uniquely associate it with this factor. So this diagrammatic element is equal to negative m over 2 pi h bar squared, Fourier transform potential of k2 minus k1. Likewise, every time I have a propagator, something that takes me from one vertex to another vertex, I will always have the Fourier transform Green's function. So I will always have, anytime I've got a propagation with momentum h bar k prime from one point to another point, this part of the diagram is equal to negative 4 pi over k squared minus k prime squared plus I epsilon, where k squared is the real true energy, k squared is 2me. K prime is whatever's happening in between. And the last piece is, after you construct these products, integrate over all undetermined momentum. So these are the Feynman rules. Feynman rule number 1 for the potential, Feynman rule number 2 for the propagator, and Feynman rule number 3 is integral d3k prime over 2 pi cubed for every undetermined momentum. Undetermined or unconstrained. You'll sometimes see it referred to as a loop momentum. I guess it's worth pointing out that at the endpoints of this, we have the free particle states. So we have something like e to the plus I k incoming dot r initial for the incoming wave. And I have e to the minus I k final dot r final, whichever coordinates you're calling it for the outgoing. So understanding how the Green's functions build up series of integrals and then converting those things into momentum space breaks it down into a completely identifiable product of factors that you can write out unambiguously. So rather than repeating the entire calculation, I can immediately write down the answer for the qubit contribution using the Feynman rules. The contribution to the scattering amplitude f of q at order v cubed. This is represented by this diagram. One potential, two potentials, three potentials. I end up with momentum h bar k final. I came from h bar k initial. If in between I've got h bar k prime and h bar k double prime, then the momentum that came in from the potential is h bar k prime minus k initial. This one is h bar k prime, k double prime minus k prime, and this one is h bar k final minus k double prime. So I can immediately write down the answer that this is equal to integral over the two undetermined momenta, k prime, k double prime. And then I read off the diagram. For the final state, I have e to the minus I, k final dot, scratch this one. We Fourier transformed over this. This does not exist anymore. This is here in position space, but we already used that in going to momentum space. Excuse me. So I start off reading the elements here. For this vertex, I have minus m over 2 pi h bar, Fourier transform potential, k final minus k double prime. For this propagator, I have minus 4 pi k squared minus k prime squared plus I epsilon, double prime squared plus I epsilon. For this vertex, I have minus m over 2 pi h bar, Fourier transform potential of k double prime minus k prime. Then I've got another one. For this propagator, I have minus 4 pi over k squared minus k prime squared plus I epsilon. One more vertex and I'm done. Minus m over 2 pi h bar, Fourier transform potential, k prime minus k initial. And that's the whole thing. So if we were dealing with the Yukawa potential, for example, then this Fourier transform potential would have a simple form. It would be 1 over this momentum squared plus q squared times some factor. And you can build up the integrals in momentum space in a much more directly doable way, in a way that immediately generalizes to anyone. So the point of all of this discussion is to show you how to go beyond just the Born approximation. This is just the starting point of a general treatment of scattering theory. But that the scattering theory treatment is systematic. And you do that by applying the Feynman rules in momentum space, that it is so systematic you can enumerate exactly what you have to do and start drawing pictures, because the pictures have a one-to-one correspondence, every element, with the answer you would get by doing the brute force calculation of working out the Green's functions. So my point here is to help you understand and place this in context about what the physics is and how the approach is systematically generalizable. Again, for your practical purposes, the thing that you will need to do under pressure is just the Born approximation. You will need to be able to take a potential that is given to you on the comprehensive exam, Fourier transform it, plug it back in and get a cross section. But for your long-term context of how this fits in physics and how you will use this in research someday, maybe, this fits at the beginning of the perturbation series, which is constructed systematically in this way. Okay, I'm out of time. There are a few other comments to make about the validity of the Born approximation. Now that we know that the Born approximation is just the lowest order in perturbation theory to something which is much more general, we should discuss when the Born approximation is a good approximation. That will take a few minutes on Wednesday, and then the last topic of discussion is phase shifts and scattering lengths. Any questions or comments? Okay, thank you guys for your input first thing at the beginning of class about plans for the exam and homework cutoffs and things like that. We will continue the discussion. I will post this on Canvas and solicit further input from people to make decisions about what we'll do going forward. Any questions before we adjourn?
Thank you, Professor.
Thank you guys very much. See you on Wednesday.